Greetings, Graham Warren, working with you on the ACG simulation model, Antico Cafe Greco. So, we've got two alternative tools for working on this case, queuing theory and simulation model. You're being given the simulation model because although AnyLogic is a sort of a no-code, low-code graphical type tool, the curve is a little steep given the kind of time that we have available to put into projects like this. So I'm giving you the tool, and this intro is going to just elaborate what this all means. Then I'm going to come back in a separate video and try and replicate the analysis that we did for the queuing model using the simulation model. Queuing gives you steady state results or sort of long-term average results. The simulation model gives you transient results, sort of like short-run results if you want them. But what we're going to do is we're going to use the simulation model to sort of investigate long-run steady state behavior or average behavior, so we can compare what we're getting with the simulation model to our queuing results. So we're using the one tool to validate the other directly. So we're going to spend a week looking at the AnyLogic tool and building this up using a variety of demonstrations. There's a source block here, so I'm just going to jump right in and explain how this thing works. When you look at the palette here, there's a process modeling library. Let me see if I can find it. Process modeling, there it is. And you can get most of these blocks from this process modeling library. So this is a discrete event simulation. And discrete event simulations are appropriate for the ACG setting because what are important here are things like an order being initiated, an order being started, the coffee making process for the order being started, and the order being completed. These are the three major event types, and they're discrete. So we don't have a lot of sort of agent interactions or flow type behavior, which would argue for other model types. So our main events are going to be sort of the basis for this diagram that really is the model. So we have customer arrivals. Now we know that they arrive in our setting here at the rate of 105 per hour. And I'm going to just click on this so you can see the details here. And I'm modeling this as a Poisson process. So you can plug in arrival time distributions, and there's a variety of options here. But if I just choose rate and an arrival rate, which I'm going to specify elsewhere, you can see I'm specifying it here, then I get a Poisson process. I'm not allowing myself to have more than 50,000 arrivals because I am using the free version of the software. And I am on, well, it doesn't show here directly, but let me just see which version I'm on. Got AnyLogic. I'm on version 8.9 currently, and you should be on that or higher. So because it's a free version, it's limited to 50,000 arrivals. It has to be some limitations for the free version. The professional version is infinite, but also a lot higher in cost. So we're fortunate to be able to use this rather sophisticated tool for free. So that's the arrival process of customers. I'm going to skip the time start. There's a timer that I'm interested in. Really, I'm just using the timer to figure out, timing system. But let's see what happens if I just ignore that. I'm going to grab a server. Server is a barista, okay? And I'm going to click on that. Now, you're going to specify how many you want here, but not directly. So I'm using a resource pool called servers, and I will specify the number of servers for this resource pool in the resource pool block. So I'll get back to that in just a second. But I'm grabbing a server here. I'm just grabbing one, as you can see. And then once I've got that server essentially comes with a Venus Arduino bar, and they can make the coffee. A little bit of a delicate issue here. You'll see I'm using a normal distribution. It's got normal, but I've got these two parameters that may look a little odd. You can see about the mean service time and the standard deviation. So that's something you'd expect for a normal distribution. What's the zero and the infinity? Well, what I want to do is, because I want to have some scenarios where I have high variance, like in our case, we have a standard deviation of 100 seconds if we don't have trained baristas. That could create negative times. If you think about the normal distribution, it's centered at 65.45 seconds. You're easily going to, blow past zero here with a standard deviation of 100, right? So to ensure that we do not get negative times, I'm going to cut this off. Truncated normal is what I'm dealing with here. On the top end, it can go all the way up to infinity, right? No problem on this. But I do want to ensure that I'm not getting negative times. So this is actually a truncated normal distribution. And the results we're going to get when I have high standard deviation are actually conservative, meaning the waiting times will be higher than what they will actually be in practice because of this truncation. I'm not going to do any correction for this. I'm just going to use it because I don't want to have, it's a quick and dirty approach. I do not want to have negative service times, hence this is zero in there to truncate the standard normal. Okay. Let's see what else we've got. So now we've made the coffee, it takes a normal amount of time, then I'm releasing my server. And then I have this, just ignore the timer again. I destroy my customer. Okay, the order came in, I got the barista, lined up, made the coffee, delivered the coffee, end of customer, right? And of course, customers are going to keep on arriving at the rate of 105 per hour. Now, this timer, I want to start the timer just after arrival and after the coffee is made and the barista is released. These will happen concurrently, really, in practice, right? You finish the coffee and the barista's proceeds. You could have put this time measure in here in this sort of little workflow, but it's going to not be any different. Now, let's have a look at this server, this resource pool for servers. The capacity here is number of servers. So what I've done is I've created this list of parameters for the model to sort of have in a single organized place all the key parameters that you're going to need. So all you're going to need to do ultimately is to change these values here to investigate these different scenarios. And number of servers is going to be, in the base case, 3. If you're not pooling, be 1 and so forth. We'll see how that changes as we go. Finally, I've got some statistics that I'm collecting, the queue length, server utilization. We're expecting to see 63.46% in most of our scenarios. If we go to 4 baristas, it's going to be below that. If it goes to 2 baristas, it's going to be at, 95 and change percent. Something to worry about, think about at least. And then if we go to 1 server, it's like at 1.9, 190% utilization. That person is not able to operate the restaurant alone. So 1 server cannot work. And then I've also got the histogram of the waiting time in system. I've got it listed here as W sub Q, but really that should be, let me just make it W sub S because it really is W sub S. Change that. There we go. Right. Let's, a couple more things I want to just point out to you that you're going to need. So if we go to projects, I'm going to go to simulation main. You can see our parameters are located here. The mean service time is 65.45 seconds. The arrival rate 105. Here's the standard deviation of the service time and the number of servers. I'm going to run it with 3. That's the base case. And one other thing that's important in simulations is that, especially if you have high variance scenarios like the untrained barista scenario where your standard deviation is really bounced up from like 10 seconds to 100 seconds, you're going to have to do multiple runs. So I want to show you where you can use the same parameter settings, but use different random number generations. Okay, so it's also in simulation main, apparently. Where is randomness? Here it is. Just change the seed to any other integer. It just has to be just some other number. What this does is it sort of starts the random number generators in a different place, and you get a different time evolution of the system. So, one way of thinking about these runs is, if you came in, let's say, August 2024, and you observed the system, you get a certain expected waiting time, time in system rather. Come in back in September, redo that whole thing, redo your study, get a different number. So that's what this changing the seed value does, is it essentially gives you a different time evolution of the system, because you're resetting the random number generators that are underlying all of these distributions, like the inter-arrival time distribution and the service time distribution. So have a quick look at this, how this runs. One other thing I forgot to mention is a little animation piece here, and you'll see how it goes in just a second. It's not very fancy, but these are the actual coffees running from order arrival to completion. So while they're going here, they're being made. You can see, and this is how many orders have arrived. This is, how many have completed seizing of a barista, how many have been made. Here you've released those servers again, and how many have completed the whole process. You can see your queue length is low. There you can see how many servers are being used at any time. 1, 2, 3, sometimes 57% utilization currently. You've got an estimate of W sub S here, 1.21 minutes. From our queuing analysis, I think we agreed that this should long run be about 1.3 minutes. We'll see how that goes in just a second. You've got a nice summary of your parameters. Arrival rate's 105. Mean service time is 65.45, standard deviation is 10, and then there's 3 servers. So this is your sort of running screen, and you can play around with this. You can accelerate it a little bit, speed it up. Now there is a limit of 50,000 customers or instances, entities in this system, and if I look at I'm as a time basis, I'm using minutes here. So if I take 50,000 divided by 105, let's do that. 50,000 divided by 105, because that's how many arrive per hour. I've got 476 hours of simulation time that I can simulate this system before it crashes. So I could go up to 28,000 minutes. I'm going to just simulate it for you for 25,000. So to do that, I go to where this little gear wheel is, and I click this ellipsis here, plug in 50,000. And you can see it's currently at 340 minutes. I want to simulate it for quite a long time. It has to appear in red. So you plug in 50,000, hit enter, so you get it in red here. And then you can accelerate all the way to the end fast. Let's see, ultimately, I'm going to generate there is 50,000 customers. Well, I should have simulated for 25,000 minutes. My bad. But in any case, the average waiting time in systems 1.31 minutes, which lines up with what we did in the queuing. Okay, that's the base case. That's the model. I will end this one here and then come back in a separate clip to look at those process innovations.